let's go on then and figure out how to calculate that other number called atomic mass. Okay? And so atomic mass, as we said, is an average, but it's not just a normal average. Right? Let's take a look at carbon, for example. Carbon exists as 12 isotopes: carbon-12, carbon-13, and carbon-14. Right? Masses of each of these isotopes aren't exactly 12, 13, and 14. They're really, really close. Right? And so for math class, you know that if you take the average of those three isotopes, you get an average mass of 13. However, we know the atomic mass is written on the periodic table, so we look at the periodic table, and lo and behold, number 12, number 6. Number 6 carbon has a mass of 12.01. What the deuce? How on earth do you get an average mass of 12.01 when you have 12, 13, and 14? Well, what the deuce is that this is what's known as a weighted average instead. So just as your end of the semester is weighted, say, 80% in your classwork and 20% on the final, where you get more, basically your classwork counts for more than your exam does. So here, what we do is we weight it according to how common the isotopes are. So in this case, carbon-12 is by far the most abundant isotope out there you're going to find. If you pick up a random carbon atom out there, it's probably going to be carbon-12. There's just a tiny percent of carbon-13 and a tiny percent of carbon-14. And so it doesn't seem fair to say the average mass of carbon is 13 when there's hardly any carbon-13s out there, or carbon-14s. Most of it's carbon-12. And so we skew it heavily towards carbon-12. In fact, it's about 12.01 then. Right? So the way you actually calculate it is you would say your atomic mass is equal to the mass of the first isotope times the percent abundance of that isotope and that's in decimal form, so 80% would be 0.8, not 80. And then you add to that the exact same thing for the second isotope. So you do your mass times its percent abundance, and then you keep on doing that for all your isotopes. You add them together. Right? So you get the hang of this, and it's not real difficult or real commonly tested either. So let's look at silicon. Silicon exists as 3 isotopes. Most of it, and over 92% of it, is silicon-28, which actually has a mass of 27.98. The reason for that is because of Einstein's relativity. Some of the mass is converted to energy and released. Think of an atomic bomb. Some of the mass that was in the bomb is released as energy, not as mass. Right? Silicon-29 is another common isotope. Well, not really common. And then, which actually has a mass of 28.98. And then lastly, we have silicon-30 with a mass of about 30 here. Okay. So let me go ahead and color code these to make it a little clearer. So we have our more common blue isotope. We have our lighter red isotope. And sorry, that's heavier. And then our even heavier green isotope. If you notice there, we're missing its percentage right there. Okay. So 3 isotopes, we know the mass of all 3, we know the percentage of 2. So first thing, how do we figure out the percent of the other one? Well, of course, percents. Think of a pie chart. You got 3 different slices of pie. We know one of them is 92.2. We know one is 4.7, so what's a mystery slice? Well, you just subtract it from 100, and that's how you figure out what's missing. So 100% minus 92.2 minus 4.7 will give you the missing one of 3.1%, right? Okay. And so we'll put that in green right there then. Okay. And then next we want to calculate the atomic mass of silicon. No cheating. Just look on the periodic table here. You actually have to calculate it. Okay, so our atomic mass is going to be equal to the mass of the first isotope, which is 27.98 AMUs. I forgot the AMU here. That stands for atomic mass unit, which is the mass of a proton or neutron. They're slightly different in mass, but they're close enough. It's a lot easier than working with kilograms because the mass of a proton is really, really small, as you can imagine. Don't confuse an AMU with an EMU, which is an emu, which is a large flightless bird from New Zealand and Australia. Two totally different things. Learned that one the hard way. Anyway, so the first isotope has a mass of 27.98. We're going to multiply that by the decimal version of its percentage, which is 0.922. Let me go ahead and do that. And so that gives us a contribution of 25.80 AMU from the first isotope. Yep. The next is the red isotope. So we're going to add to that the mass of the red one, 28.98 AMU. We're going to multiply that by its percent abundance, which is 0.0470, if you want. And so when we multiply those, we're going to get a contribution of 1.36 AMU. If you're following along in a calculator, you'll notice you get a lot of other decimals. Later we'll learn how to round, how to deal with those decimals, but for now I'm just going to use 2 decimal places too. Then lastly, the third isotope is 29.97 AMUs times its percent of 0.031. And so that's going to be 0.93 AMU, basically. Okay. And so lastly, we're going to add up all 3 of those masses down below. And when we do that, we get 28.09. And we can check ourselves in the periodic table. And sure enough, the atomic mass of silicon is 28.09. So it's a good way to check yourself. You might be wondering, why on earth do we have to do this if we can just look on the periodic table? Valid question, but we do it anyways. Okay. I'll let you go ahead and try number 2 here. The difference here is that we don't know the mass of the second copper isotope, and so we got some different unknowns, but the exact same process in reverse, basically. So I'll let you work it out here, and I'll meet you back here in a second. Okay, here, so we know the mass of one of our isotopes and its percent. Now we have 2 unknowns. We don't know the mass of our second one, nor do we know its percentage. Okay. But we can figure out the percentage pretty quick, right? Because if it's not one, it's the other. So we can just subtract the 2 percentages, or subtract the percentage from 100, and we get a missing percentage of 30.91% then. Right? So that was easy. But what's the mass of the other one? That's going to be a little bit trickier. We are missing a piece of information here, and that is the actual atomic mass of copper. What is the average mass of all copper atoms? We do actually know that because we know the periodic table. We always got that. And so we look on the periodic table, copper is number 29, but its atomic mass is 63.55. We're going to go ahead and write that. 63.55 is our atomic mass. That is going to be equal to the mass of the first one, 62.93, times its percentage, 0.6909. And then we're going to add to that the mass of the second one, which we don't know. We'll just call that x, multiplied by its percentage of 0.3091. And then we solve for x and see what we get. Right. So this is going to be 43.4748, and then this, of course, would be 0.3091x. I solve for x. Hold on just a second. And you get 64.94 AMU. Okay, just a few things to note. So we found a mass of our second isotope of almost 65 AMUs here. Our mass of our lighter one is almost 63. We could have known right from the get-go that our second isotope was heavier. Well, because we know the average mass of all coppers is over 63, and the mass of the lightest one was not 63. So there had to be a heavier one here to bump that average up. We could also tell that the 63 one, though, was a lot more abundant because the actual atomic mass is much closer to 63 because it's so common. And so again, it's a weighted average, so it's going to be skewed towards the more common isotope, which is the one with the mass of 63. Now, next question, how many atoms would actually have a mass of 63.5 AMUs? Well, that would be none. Right? It's an average mass of all the atoms, not the mass of any of the atoms necessarily. Right? It's like the average number of kids in the American family is like 2.1. Right? How many families actually have 2.1 kids? Well, probably none. Right? It's just an average. Right? And so the atomic mass is just an average as well.